Good evening and warmly welcome all of you to join with a special session organized by IESL Water Forum in collaboration with Civil Engineering Sectional Committee of IESL. I am Engineer Ruchini Chandratilaka, member of Water Forum IESL. Today we are going to discuss on an interesting topic, how environmental and social destruction caused by Uma Oya Multipurpose Development Project was averted, with the prominent expert in the field of geology and geotechnics. So this is the starting session of the series of sessions on Uma Oya Multipurpose Development Project, and we are happy to announce you that you will be able to join with virtual visit to Uma Oya Multipurpose Development Project as well as online seminar to aware on lessons learned from Uma Oya project covering social, environmental and contract management issues faced and how overcome them in near future. So please connect with us throughout the series of sessions. Before proceeding further, let me kindly remind you two basic rules of this session. You will not be able to switch on your mics, cameras before Q&A session. You can send your questions to our speaker in the Zoom chat and he will answer them later. In addition, you can get a chance to speak by raising hand using Zoom hand raise option. So these are the basic housekeeping rules for the event. Without taking much time, let me now invite Honorary Chairperson of the IESL Water Forum, Engineer Bhadra Kamaladasa, to welcome the gathering. Over to you, Madam.
Thank you very much, Ruchini. Good evening, everyone. I welcome you all to this interesting presentation on behalf of Water Forum and Civil Engineering Sectional Committee of IESL. I warmly welcome Professor Jagat Gunatilaka and grateful for accepting our invitation to share his valuable time with us for this presentation. Among us the various objectives of Water Forum, peer reviewing of current ongoing projects is one important aspect we are focusing on. So we identify certain aspects of a project where engineering judgments are vital and then invite those involved therein to share their experiences. This is one of that series of programs, as Ruchini also explained. So our main aim is to develop a platform to professionals to share their success stories or maybe bitter experiences so that others can extract good practices or realize where some judgments or decisions can go wrong and went wrong. So we are more interested in discussing the issues that attracted attention of media. The reason is whatever opinions are expressed in social media may not have been based on the scientific evidences. So it is our duty to correct them. So at least awareness among our engineers must build up, especially within the engineering community of IESL, for them to talk with confidence in public when these matters are highlighted by some laymen. So further, this is to enhance their decision-making capability, especially for the younger generation, learning through these case studies. So it is not to corner. We must remember that this program is not to corner anybody who has taken decisions or to find fault with any institutions, but to open up the professional dialogue. So with that note, I would like to invite Engineer Kaushalya to introduce our guest speaker today. Engineer Kaushalya, over to you.
Thank you very much, Madam. Wish you a pleasant evening. It is a great privilege and honor to introduce Dr. Jagat Gunatilaka, Senior Lecturer, Faculty of Science, University of Peradeniya, who accepted our invitation to be the guest speaker today. Dr. Jagat Gunatilaka obtained a first-class BSc Honours degree in Geology from the University of Peradeniya and the MSc degree in Engineering Geology from the Asian Institute of Technology, Bangkok, Thailand. He received PhD degree from the Saga University in Japan in Geotechnical Engineering. He joined the University of Peradeniya, Sri Lanka in 1993 as a lecturer and promoted as a senior lecturer in 2001, attached to the Department of Geology, University of Peradeniya. He served as the head of the department for 3 years and served as the chairman of the Board of Study in Earth Sciences of the Postgraduate Institute of Science. He is the coordinator of MSc program in GIS and remote sensing, as well as MSc program in engineering, geology and hydrology attached to the PGIS. He has supervised over 250 postgraduate MSc theses, 5 MPhil theses, 1 MD thesis and 3 PhD theses during last 20 years. Dr. Gunathilaka conducted supplementary geotechnical investigations in Umaoya project, which led to changes in tunneling process to mitigate leakages through tunnels. He served as the chairman of panel of experts to advise on Umaoya Multipurpose Development Project. Sir, once again, thank you very much for accepting our invitation. Over to you, sir.
Yes. Yes, thank you, Kaushalya, and also thank you, Engineer Badra Kamaladasa, for organizing this and giving me the opportunity to talk about this topic today, how environmental and social destruction caused by Umaoya Multipurpose Development Project was averted. So I selected this slide to start the presentation because this shows the Umaoya. Umaoya is the stream in Sri Lanka that brings highest sediments into Ranthambhe Reservoir. Actually, this Umaoya has the highest sedimentation rate. So you can see how this Umaoya brings sediments into Ranthambhe Reservoir. So it sweeps all the agricultural lands in Bandarawala Valimada area and brings all this clay and silt or fertile soil into this Ranthambhe Reservoir. So as I have heard from the director Mahavali Headworks, already 35 to 45% of Ranthambhe Reservoir is filled with sediments during the last 30 years since the construction, since the impounding of this reservoir. So we were fortunate to take these photographs in during the dewatering of Ranthambhe Reservoir in year 2006, just after huge, a large number of landslides, which brought huge amount of debris and sediments into this Ranthambhe Reservoir, and it damaged the intake structures for the Ranthambhe powerhouse. So during that time, we managed to bring our students as well. So you can see the sediments, huge, thick sediments accumulated at the dam, almost close to the dam. On all the bottom outlet gates were blocked by these sediments somehow during the dewatering. These people have, or the workers, they have managed to open up some of the bottom open gates. And these are the damaged power intake structures of Ranthambhe powerhouse during that, due to huge debris brought along this Umaoya. This, the close-up view of this damaged intake structure, huge structure. Yes, now, of course, with the construction of Umaoya Multipurpose Development Project, I think the amount of sediments that will be brought, to Ranthambhe Reservoir will be drastically reduced. So this Umaoya Multipurpose Development Project is located in southeast of Sri Lanka in Central Highlands in order to transfer water to produce hydroelectric energy and to use this water to agricultural industry. So this Google image map shows the areas, and Bandarawala is at the Bandarawala and Makullella. You may remember that during the year 2004, when this huge leak was started, Makulella was the highly damaged or severely damaged area, and also Bambaragama and so on. So this project components are distributed from this Puhulpola Dam over across Umawe, and then Dairaba Dam across this reservoir, and then this 15-kilometer long head race tunnel. So all this Umawe project consists of 2 RCC dams, roller compacted concrete dams, and the first dam is built on Umawe in Puhulpola here. Then the second dam is built on Mahatotilla in Dairaba. So these 2 reservoirs are linked by the 4-kilometer long link tunnel, and the water from Umawe to be transferred to Dairaba Reservoir. And from Dairaba Reservoir, headrace tunnel is constructed up to Karandagolla, very close to Vellavaya. So this is done through 15-kilometer long headrace tunnel. So you can see the location of Bandaravella and the project components within the map. So the tail race tunnel with 3.6 kilometer length is to direct water from the powerhouse. After bringing this water from the powerhouse, water is being transferred through Alikotara, which is a branch of Kirindiwaya. So this shows the schematic longitudinal section of the project. Puhulpola Reservoir, Dairaba Reservoir, link tunnel, and the headrace tunnel, which is 15-kilometer long, not to scale, please. And then a 600-meter long shaft, vertical shaft, that is the 3.5-meter diameter, brings this water from this headrace tunnel towards the powerhouse to generate 120 megawatt of power. Then water is to be taken to Kirindiwaya through the tail race tunnel through Alikotara Reservoir. So this is the area to be catered by this Umawe multipurpose development project. The tunnels, and from Vellavaya or Karandagolla, all the water is to be taken to feed Handapanagala, Lunugammehera and Hambantota areas. This is the Puhulpola Dam constructed on Umawe, 50-meter high dam, and the link tunnel is just upstream of the dam. So you can see the link tunnel is constructed to bring the water from to Dairaba Reservoir. Dairaba Reservoir is constructed on Mahatotilla. That dam also 50-meter high dam, and headrace tunnel is started just upstream of this dam. So this is the place where headrace tunnel starts and going through this mountain, and the link tunnel from Umawe or Puhulpola Reservoir will bring water up to this point. So this link tunnel is from Puhulpola Reservoir to Dairaba Reservoir, that is constructed as a conventional drill and blast tunnel. Then access tunnel at Karandagolla to powerhouse also constructed as a conventional drill and blast tunnel with supports. So you can see usually how a conventional drill and blast tunnel is being done during excavations: drilling, blasting, and mucking. And so this excavation of the 15-kilometer long headrace tunnel, I'll call it as HRT from now onwards. HRT has been commenced in March 2014 with a tunnel boring machine from the downstream end from Karandagolla. So when excavation reached 3.8 kilometer, little less than 4 kilometer, all of a sudden excessive water ingress was encountered on 24th December 2014. So this is the portal for this tunnel. So this just to show how this tunnel boring machine is assembled in front of the tunnel that is to be constructed. So this shows the sound rock within this tunnel constructed by tunnel boring machine or TBM. So it needs it does not need any support. Rock is sound. Without support, TBM can run. And in areas where the rock is not sound or rock needs support or seepages exist and so on, supports are to be erected. Here in this TBM, tunnel boring machine, supports are to be erected from the TBM itself. They are concrete segments. Precast concrete, four segments are to be installed. And regarding the alignment of headrace tunnel, HRT of Umaoya, I have to mention that initially, originally, this headrace tunnel was designed as a straight tunnel, starting from Dairaba Reservoir to Karandagolla powerhouse, just above 600 meters above the powerhouse. It was designed as a straight tunnel as indicated in this black line. It starts again from here and going towards Karandagolla. But there were 13 boreholes drilled along this original straight tunnel trace, and with the results of these 13 boreholes, not 13, the boreholes that have been constructed within the center part of this HRT, it appears that the ground is not suitable for tunneling. So that means there are some cavities, marble or limestone, crystalline limestone cavities, and some seepage zones and highly weathered zones, and some boreholes indicated the weather overburden is much thicker than 200 meters at some locations. So then what this construction project or Iranian construction project that they did was they have just deviated the headrace tunnel by several around 250 meters like this up to this red line, deviated towards southwest. So this the tunnel TBM was constructed along this red line trace. During that construction or before construction of along this or deviated trace, it has to be mentioned that no special investigation, so no detailed investigations have been conducted, or no boreholes have been drilled along the newly or deviated trace of this tunnel, because the original tunnel trace was bad or appeared as weak geology. They have deviated along this trace without doing any additional investigations or boreholes. So this shows this TBM tunnel boring machine finishes the tail race tunnel and coming or breaking into the powerhouse cavern. So this is the TBM cutter head. So this is the construction of powerhouse cavern just after completion of several levels. Already turbine is at the bottom and generators are also fixed by this time, and generator there, and the turbines by that time it was progressing with the, and there's a vertical shaft from at the end of the HRT headrace tunnel, 600-meter long vertical shaft water from this headrace tunnel to the powerhouse. So this is the place where this HRT was excavated, and search chamber there. And the total length of this HRT, as I mentioned, 15 kilometers. And this take water from Dairaba Reservoir to the pressure shaft, that high pressure shaft, 600-meter long, high pressure vertical high pressure shaft, to generate hydroelectric power from the powerhouse. This headrace tunnel HRT was constructed by this TBM tunnel boring machine. This is a cutter head and the parts of the TBM, thrust and so on. So this is the first use of a TBM in Sri Lanka. That's why the tunnel boring machine was new for us Sri Lankans here. And it is also a double shield excavating machine. Double shield excavating machine. And this shows the precast concrete segments. So these precast concrete segments are just like a ring. It consists of four parts: inward segment and roof or top segment, and left wall and right wall segment. 4 segments. So inward segment is compulsory to be erected because all the locomotive or rail tracks are to be fixed on this inward segment. But both left and right wall and roof or top segments are not necessary if the rock is sound. And TBM has a backup system which is approximately 200-meter long, including the TBM shield area from the cutter head. Cutter head is the place where TBM is progressed. These concrete segments are to be erected within the TBM shield area itself, so that TBM cannot be reversed in any case, because once the concrete segments are erected, the diameter of the tunnel is being reduced by the thickness of the segments. So TBM has to go only to forward direction. So this backup section of this double shield TBM has, it includes electrical supply and switchboards, cooling systems, pumping units, mucking systems, segment feed systems, grouting units, drilling units, and even shotcrete units. So this is the backup system for the TBM backup. So actually, even beyond 200 meters, several compartments are attached to that. So this shows the good or sound rock. Only the inward segment is installed. Left or right walls or roof or top segments are not installed because of the rock is sound, just like exactly like drill machine drills a rock. So these are the tracks for locomotives, 2 tracks, and these inward segment, roof wall, and right wall segments. And the area or space between this precast concrete segment and the rock wall, there is some space, about approximately 10 centimeter space is there. So that has to be filled with this crushed gravel, which is called pea gravel. So this pea gravel will fill the gap between rock wall and the concrete segment. After filling it, cement grouting would be performed to fill the gaps between, fill the voids between this pea gravel. So this is cutting wheels, which are the most important part or most varying parts of the TBM. So some telescopic systems are there to push the cut to the front or to the face, and there are some thrust devices to take thrust and so on. Then the cutting material or muck, tunnel muck, is to be collected into this conveyor belt. Conveyor belt is starting from the cutter head up to the locomotives where this tunnel muck is to be filled. So this is the way tunnel muck is to be transferred to this locomotive, or this TBM tunnel muck is to be collected along with these compartments, and once they are filled, they will be brought out like this. This is the TBM tunnel muck, just like trains. All compartments are there, maybe about 10 compartments are to be filled within a day or half a day. I have to mention that at the beginning, before these problems started, so they could progress with sometimes with 40 meters per day. That's a huge, big progress for the TBM. So these are the holes to be grouted once pea gravels are inserted or pumped into this space between rock and this segment, and then it is to be grouted using these grout packers. And so far I was showing the TBM that has been launched from the downstream from Karandagolla side. So later, once the tail race tunnel is completed, that TBM, the same TBM also was brought towards Dairaba side, Dairaba end, and it was launched from that side. So it is just going inclined. Actually, this is very critical. If all of a sudden some leakage happens, water will be filled into that, so that there should be proper method to pump any leakage or seepage water out from the tunnel. But for Karandagolla side, it is automatically, due to the gradient, all the leakage or seepage water will come towards the portal of the tunnel. So this is the cutting phase. So these photographs were taken from Mr. Lees, who was the consultant there. And from the cutting phase, sometimes if there are several, even fine fractures, because of the pressures, water pressures, this water just gushed out from these fractures. So this shows the such seepage through fine fractures in the cutting phase. And since there was a seepage, to work with seepage or leakage into the tunnel, they have constructed several drainage holes along the TBM. So these shows these drainage holes. They reduce the water pressures on the ground. So all these are drainage holes to bring the groundwater into the tunnel. These are also drainage holes. So not only leaking water, so these drainage holes also will bring huge amount of water into the tunnel, like this drainage holes, left and right holes, all this going through the portal of that. So flow rate of the leakage in HRT were measured from 2014. I mentioned that first water ingress, considerable water ingress was appeared on 24th December 2014. During that time, it went up to about 450 liters per second. So on, and it was reduced up to about 200 liters per second or even 100 liters per second when the tunnel was progressing. And on June 2017, again, it has been rose up to maximum level, that was 1,300 liters per second due to this main water ingress in year 2017. It was reduced like this up to 2018. So the maximum water flow that has been observed along the HRT was 1,350 liters per second. So with this leakage, so there are environmental problems. So many of the dug wells were dried up and houses began to be cracked due to settlement and all this. So with that, panel of experts was appointed by engineer Nihal Rupasinghe. Then he was the secretary to the Ministry of Mahaweli Development and Environment. And I happen to be the chairman of this panel of experts with this team from NBRO, CECB, Dr. Jayatissa, Mr. Ken Bandara, Mr. K. Jayatilaka from CECB, Engineer Pulgunasekara, CECB, Engineer R.N. Pereira, Darshana Abesinghe, Chinta Kamarasinghe, and Professor Navaratna, Professor Dharmagunadana, and Engineer S.K. Javardhana. So these 12 panel members, we worked hard during the first 2 months to find what was the reason and what can be done to arrest these seepages or leakages and to advise the project. So that was our mandate. So during the studies, actually, it was identified that this water ingress event started when the tunnel was in progress about 350 meters above the tunnel heading. Actually, within the day itself, the dug wells 350 meter heading started to be dried up. So the effects, environmental effects identified were lowering of groundwater levels. So some of the dug wells were completely dried up, drying of many dug wells, drying of few natural springs, and drying of some watercourses, and minor or major cracking of walls and floors of some houses, buildings. Just on the following day itself, they started to be cracked. So river holes and some sinkholes collapsed, and ground cracking also was observed. So then the geological mapping, actually as a recommendations of the panel of experts, detailed geological mapping along the deviated tunnel trace has been carried out. So University of Peradeniya Department of Geology was involved with it, and the team of about 60 geologists and trainees, they joined the operation and did this geological mapping, engineering geological mapping along the headrace tunnel, along 1 kilometer corridor, 500 meter northeast and 500 meter southwest directions. 1 kilometer corridor mapped in 1 to 1000 scale. That's fairly detailed geological mapping. That is the must for such tunnel excavation, tunnel investigations. So geological profile was created like this. So you can see the red line indicate the tunnel trace, tunnel level. And here from this side, we can see how the geological formations, the forms, synforms were there, and the rocks, particularly Charnokitic gneiss, quartzites, and more importantly, this pink color rock is condylite. Condylite rock has a characteristic feature of deep weathering and fast weathering. We have encountered the same problems in Samanalawava project, even in Kaluganga project, again Umawe project, and projects. This deep weathering has brought several geological problems. So this shows the part of the maps. This yellow indicate quartzites, silica, SiO2 rocks, and then this purple color, Charnokitic gneiss, fairly good rock, and garnet biotite gneiss, like that. So example of how this condylite rock get weathered. This example is from Samanalawava. So condylite rock, when they were excavated from the quarry site, it was fresh, sometimes somewhat pinky appearance is there. So all these fresh rocks have been completely weathered within the first 10-15 years time now. Even if you go to Samanalawava Dam, even today, you can see some blocks of these rocks are completely weathered or transferred into soil. So some of the rock bands in the adits, grouting adits or excess adits, they are weathered. So you can see only these condylite rocks are fast weathering. Not only that, huge damages to the tunnel walls or adit walls can happen due to this condylite rock weathering in Samanalawava grouting adits. So similar rock is there. We have identified this condylite rock along certain sections of the HRT. So not only that, there are during the hydrogeological study carried out on the tunnel trace or deviated tunnel trace, deep well water levels were studied and shallow well water levels also were studied, and also seasonal variations and water ingresses were studied during the detailed study. And it was identified that water ingress caused mainly through geologically weak zones like lineaments, joints, and fracture zones, and also deeply weathered rocks, as I mentioned, condylite. So here you can see major lineaments are crossing the HRT trace. This is the head-race tunnel trace. So you can see major lineaments like this are crossing the HRT. So definitely we could identify that this is one of the definite location where leakage can appear. So lineament mapping has been done, and then together with geological mapping. So here you can see clearly how these lineaments are crossing the tunnel trace, and these streams are also mostly aligned along such lineaments. So in other than these lineaments which are crossing the tunnel trace, there are lineament of along Mahathati lower, which is parallel to this tunnel trace. So that brought huge problems into the tunnel because all the areas were drained into this tunnel. All these streams were drained into this tunnel through these lineaments. So for example, this at Palliperu area, between 8 plus 800 and this chain age. So the lineaments are identified like this, and chain age 7 plus also we have identified this chain age lineaments. So we could predict that that was after this huge disaster occurred. We could acute the exact chain age will the next leakage. So then the TBM could stop few meters ahead, and they started doing probe drilling and pre-construction grouting and so on. So by doing such very effectively, once the locations where seepage or leakages will appear, they can measures very effective. So with such effective mitigation measures, the balance part could have been gone without much troubles. But obviously, progress was fairly low, because in these areas, before this problem happens, they could contractor could achieve the progress of 40 meters per day in some days, of course. But thereafter, some days only 1 meter a day or less than 1 meter a day, like that. So I'll show you some presentation of the geological map we have made. Right. So this was the time after completion of this geological mapping of along this 1 kilometer corridor, and also after construction of the engineering geological profile. Along that, we have presented it to the foreign expert who were brought there, and even local experts and the contractors were there. So you can see the geological map and the profiles. So this part is the deviated section of the tunnel trace. So I will make them right. Right. This is the Professor Senaviratna is there, Professor Somaratna also there, and Mr. Kul, Engineer Kulnasekara, and project director was there, and the Iranian contractor, the expert from contractors, and chief routing consultant from Hamburg, and the other. These two are the who were brought there to identify the problems and to discuss the mitigation measures. So this was the map that we have prepared, we have compiled. For the foreign experts. Right, I'll go back to the slide show. Right, so for example, this yellow line is the tunnel trace. So there were some boreholes drilled, DT9, DT8A, DT8, like that. So this, for example, DT8A showed huge cavities underneath. So that is due to dissolution of crystalline limestone, which we call marble cavity. So what happened when the proceed or tunnel is progressed beyond that point was the water level, piezometric level within such boreholes were drastically dropped by up to about 80 meters or 75 meters dropped. In case of DT6 hole, dropped drastically about 65 meters. So you can see it is major water ingress location around DT6. So there were about 240 dried domestic wells within 500 meter each corridor, or 1 kilometer corridor of the area. Most of the dried wells are located on condylite rock, type of rock that I have mentioned, having characteristic deep weathering, because the weathering depth of this condylite area extends even up to 200 meters and so on. So dried up domestic wells are indicated in red color, in red dots. So they are the distribution of these dried up domestic are exactly same as condylite rock within the geological map. So there were more than 1,200 domestic wells within the area of influence. And also, interestingly, not only the wells in the vicinity of the tunnel trace, or 1 kilometer corridor of the tunnel trace, some dried wells even 2.5 kilometers away from this tunnel trace, like this. In Makullalla, Vanasirigama, Heeloya, Palleperuwa, and Egudagama area in 2016, these dried wells could be located, could be identified even beyond 1.5 kilometers away from the tunnel trace. So this how weathering in condylite could be observed in deep dug wells, but until this tunnel was excavated, these dug wells yielded water. This condylite, deep weathering in condylite. So these are also dried up wells. This was a common feature in everywhere where the condylite rock appears. But in the very nearby areas, if the surface rock is nice or charnockite, we could clearly observe that wells are not dried up. They yielded water. So that was not connected to the tunnel trace. That's what happened, tunnel depth. So progressively cracked. So on the very first day when they were only hair cracks. So second day, third day, they could observe the cracks are widening and continued even along the ground. So on the floor of the were cracked. So these progressive cracks on houses ground by settlements due to decision of groundwater. So there were some houses severely damaged and were evacuated due to settlements due to rapid depletion of groundwater table or draining the groundwater into the headrace tunnel. And also ground cracks were developed and widened, and some sinkholes in Bambaragama area. So those sinkholes are more 40 meters. Sometimes some tall trees were completely buried within these sinkholes, and part of this house was buried or collapsed, and went into the skin. So tall trees were, so the people fearing that this would continue, they have removed their roofs and they have evacuated. And these are the examples of boreholes, angle or inclined exploratory drill holes near the sinkhole, which is drilled this point. So they knew that there's a deep this borehole to 300-meter depth. So cracks could be observed in almost all the houses constructed on condylite rock. So these streams, and more interestingly, this Badulla Road, when this tunnel is crossed Badulla Road, that place was also fairly, this was identified as a lineament. So this lineament, to check the underground conditions, borehole was proposed, and this particular borehole was constructed vertically. So I remember during the time we suggested that, we predicted that this is the point where we definitely get leakage. But during the drilling of this vertical borehole, they have found very sound rock, no much and so on. Problem was, in such cases, we should have proposed angle or inclined boreholes for these locations, because the fractures or fracture zones or joints are almost vertical, more or less vertical. So chances to find these fractures through the so because of that mistake, again huge water ingress was appeared within the headrace tunnel, and again the tunnel excavation had to be stopped and stopped for several days. So that is mainly along the below this Bandarawala Badulla Road is also crossing that point, exactly that point. So have been used by Amberg, that is tunnel seismic prediction. Use this tunnel seismic prediction to predict the rock conditions ahead. So they have mentioned, or they this TSP can look about 150 meters ahead of the face from inside the tunnel. So this TSP uses small explosive charges to create a seismic waves and their reflections and structures ahead with these structures. So until such time, only 7 probe holes could be drilled on the boring machine. There were no provision boreholes for the lower part, lower half of the TBM. As mentioned, pointed out that not only this upper side, so it is essential to have probe holes or provision to drill probe holes for the TBM. Then the both had to be modified. Manufacturer from Germany, and so for these modifications, it took several months. So all the tunnel excavations had to be stopped during that time. Anyway, after these modifications, there are enough sufficient provision holes to be drilled. So this is the cutter head, probe holes to be drilled from this side. It has certain angle, so that up to this point, they had to drill, and beyond this, they can check the rock conditions about 50 meters ahead. That is well enough. Rock conditions. So probe drilling is carried out by a dedicated percussion drilling mounted on the TBM behind the tail sheet. These are the ingress in April 2017. Both TBMs permitting an increase in the number of pre-excavation grout holes. Originally, only 7 were there, so it's up to 26 in the from Karandagolla, TBM from Karandagolla, and from the TBM from 1 probe holes facilitate drilling 31 probe holes. That the TBM was modified. So, however, with this increasing drilling, excavation grouting, the excavation rate was significantly, although ingresses were avoided. Or it was drastically reduced. So this shows the outlet 26 probe holes, full circle after modification. Inlet TBM from Dairaba side, 31 probe drilled. So this is the way these probe holes can be drilled in different angles. So actually, the first drilling, probe hole drilling started in September 2016, and since then the rise of the length of probe hole drilling could be observed by the time July 2018. So this is the rate of drilling probe holes, and it is the concept that this is the construction is completed to be constructed circular or radially into the rock, and that 4 meter to be grouted. So by doing that, it is assumed that this rock mass is perfectly grouted and no more seepage of water. So to measure them, some manometers have been installed, measure the ground water pressures, and it was observed that some fractures which were grouted by pre-excavation grouting, they were properly grouted. So on panel, they could observe these certain fractures are perfectly sealed, whereas some are not such perfectly sealed. And also conducted some surveys, resistivity imaging surveys along to predict the possible deep extending weak zones. In so 80 the chain conducted such seismic imaging, identified at this point the weathered rock, that is condylite rock, the rock exceeds even beyond by the borehole drilling in weathered rock extends even beyond 195 meter, 195 meter tunnel depth. Even at the tunnel depth, no rock, only soil. So that is deeply weathered condylite in Palleperu area. Not only that, the fractures and weathering along such fractures, folds and joints be observed even at the depth of 400 meter from the surface. So weathered zones and seepage occurs along these folds and foliations. Indicate the presence of fault zones and open faults, and post-excavation grouting. Once the past the leakage locations, post-excavation grouting could be continued. So it's inserted or pressurized, pumped into these holes as grouting. But the problem, they could not increase the pressures beyond 20 bars, because the 20 bars is the maximum tolerable pressures for this precast concrete. So, on the other hand, has outside water pressure bars. As it was, and at some locations, some faults or fault gouge areas were grouted, but only lenses of grouts are remaining. Still, the clay part has not been removed. So these can be, again, these are not properly grouted. That's what. So fault filled with thick clay was encountered. So these experiences during the investigations for Gingnilwala diversion tunnel investigations, we could predict, we could suspect certain locations, and when we drilled boreholes, we could observe at Nampanagala tunnel trace, we could get is still gushing up. Even now it is already 3 years, still the same amount of water is coming out from the hole without any pump and so on, artesian water. It goes, when we fix a tube, it goes approximately up to about 12-meter height. Now, crossed these hydrogeologic conditions, huge disaster would have happened. So that's the purpose of identifying such problems during the investigations. The cost or the amount of money that is spent for such feasibility or investigations would be paid, because actually, on the other hand, proper or details have been carried out tunnel trace of Umaoya. Those environmental disaster and huge cost would have been only few tens of millions of rupees of cost for this investigation, but they had to spend more than several thousands of millions to cover the damages and also the project cost and also the delay costs and so on. So that's why detailed investigations during the feasibility stage is a must. And also during this, just before starting this mapping program and all this, to locate tunnel trace on the ground. Then even the people there, they could identify that exactly where the tunnel is, which depth the tunnel is going at these particular locations and so on. So these pegging along these tunnel traces. Yeah, and then of course during the we are carrying out feasibility studies, some feasibility of the Candy Tunnel trace. So there we have identified some of the investigations are compulsory to predict what will happen during excavations. So these are some tunnel deep core drilling and detailed geological mapping up had been carried out. And now, of course, with all these studies, detailed studies, propose that the project can go ahead without problems. And in case of Kaluganga dam project also, there were such problems at the last minute. During the excavation of the foundation, they have encountered certain karstic features. So here, until that time, nobody knew that these cavities are there. So you can see these which had to be treated along the dam foundation. And there also in Kaluganga also this condylite with prominently seen. Condylite rock, garnolitic gneiss, right. The iron, bleach out the iron from the rock, so you can see precipitations are all over. And in the hydropower project, we have seen such along the grouting adits of the same problem as and the Samanala leaking water. This is the place where water coming out. And in Samanala also there were huge cavities in marble rock. So 4-story equivalent to 4-story buildings or height. And falls even whole. We could observe some faults. This is a condylite rock. In condylite rock is filled with grouted cement, and this rock is partially filled, or the pore spaces were partially filled by grout. Samanala, just to show huge cavities just upstream of the dam along the Valavega cavity is Belihulloya and Valavega. So these during the construction of Samanala project, this is the diversion tunnel of the core fields to be done here. Then here this marble band is going there, and here again. So at this point, if somebody make a drill hole, the thickness of the marble band is even more than 26 meters. But just beyond that, if the drilling continued at this point, it is only less than thickness rock band. So that's why the geological investigation should be in very detailed. So it can't. So here also, this marble band is getting thick and thin. So these are 4 grouting adits. Ruanpur Express, we are working on that also on the 3D model. So long crossing. So these days we are avoiding segments for double cuts, and we are going to propose, or we have proposed some tunnels, short tunnels to avoid lineaments. So at last we have to mention not very appropriate actually. Several borehole drilling have been carried out along the original trace, but the deviated the boreholes have been done. So original we say that original trace would have been better because we knew that these are areas and so on. But here deviated trace, no information was there. So until it happens, we do not know the situation. Yes, that's what I want to make as a presentation. So, Engineer Badra Kamaladasa, Badra Madam.
Yeah.
Yeah.
Thank you very much, Dr. Gunathilaka. That is a very informative presentation. So it's a very with a very rich material, and I think you had organized your slides so simple that anyone can understand what has happened and realize what would have been done. So, I mean, you have shown your colors as a popular lecturer among the students. Congratulations. It was, the presentation was so simple, and we could, any could follow, anyone could follow. So, among the many things you discussed, one simple, very striking point to me to take home as a message I got was the marking of the tunnel trace on the ground, so that the society, so the people who are in, who are unrest, I mean, under many misinformation, can realize what whether they will be affected and any future hazard that they may face. So, Dr. Jagat, there were many questions in the chat box you can see, and Mr. David, Engineer David, had answered most of the questions. May I repeat those things again? Can you see the chat box? I
Yes.
can, yeah.
Going to
yeah.
on Umawe problems, of course.
Yeah, that's right. Yeah, there were about 9 questions actually I have noted down, for which most of the things were replied by Mr. David. First question was related to Umawe, how the tunnel boring was advanced in any weak rock zone, highly fractured, weathered encounter in any of these projects. So that is the question asked by one engineer Atapattu.
Yes.
And Engineer David has replied it anyway. Can you see that?
Yeah.
Dr. Jagat?
Yes. Can you hear me?
Yeah, no, we didn't hear your answer yet.
That's the problem with the. Now, can you hear me?
Yeah, can hear now. Yes.
Right. Okay. Yes, I couldn't get Badra madam, can you repeat it?
Yeah, actually, sorry. Can you please introduce Mr. David, who has answered the questions?
Yes.
To get a bit of
right.
yeah, please.
Yeah, Mr. David, I will show his face also. It is shared now, no? Right? Yeah.
Okay.
David Lees, very soon he will become Dr. David. He was the of the Umawa Headrace Tunnel, and presently he is the PhD student of the University of Postgraduate Institute of Science, and I myself and Professor Dharma Gunawardena are the supervisors of his PhD thesis. So he is a real student, of course, I would say, even though he is a chief site supervisor.
Okay.
Prefer to answer some of the questions. Yes,
Okay.
Mr. Lees. Mr. David.
Yeah, Dr. Jagat, until he comes online, there is an unanswered question. The last question actually asked by Mr. Pasan Herak. The geophysical investigations at HRT, UMDP have shown promise in identify weak zones. In the Sri Lankan context, why do we not use them in the design feasibility stages to identify potential weak zones before carrying out the drilling, which is very expensive? That is the question we ask.
Actually, that's a question that common for all of us, for all our feasibility studies. I would say that actually that is really important to do geophysical investigations before carrying out this very expensive deep drilling and all this. I would say in Kandy Tunnel project, we have followed that. We have done by detailed geological, engineering geological mapping, we have identified some weak zones, and then along to confirm those weak zones, we have done some resistivity profiling and some VLF profiling, all geophysical investigations, and then we could confirm that these locations are really really weak zones and so on. To confirm them, of course, somehow we need to know the real rock conditions at the real tunnel depth. So for that, we had to start drilling. So these days we are progressing with these such drilling, followed by geophysical tests. Yes, Dr. Pasan, yes, it is correct.
Yeah, there is a question just posted now by engineer Lalit Karunathila. Can you see that question in tunneling?
Yes, in tunneling, it is important to have details pre-investigations, identification of affected zones in different ways, water drawdown, consolidation, etc. Predetermined methods to address those issues like continuous monitoring, recharging, etc. Looks like most of these were not in place when this TBM was started. Of course, obviously, even the TBM had no provision to make such probe holes at the beginning. So only when the problem was seriously aggravated, the TBM manufacturer was brought and they were doing these modifications. By that time, environmental damages have already happened over there. So actually, if we know, if we can do these investigations before the project starts, as Mr. Lalit, Engineer Lalit mentioned, yes, we can avert most of the problems.
There's another question asking, sir, could you please share what are the methods used to direct TBM to move in the proposed path?
Methods used to direct TBM to move in proposed path. That means direct TBM, I mean, driving the TBM, or that
Yeah,
should,
it means that, yes,
yeah,
driving.
real, yeah. Actually, by doing such detailed studies only, we can really predict the real tunnel depth, real rock conditions at the tunnel depth. So with that, we can propose whatever the deviations necessary and so on. Of course, TBM has the provision to take several turns with the radius and all this. So driving of TBM has no problem. They can do very precisely. I think Mr. Lees may have good answer for that, how this TBM is directed in the proposed path.
I don't know whether his mic is muted. Kaushala, can you please unmute Mr. David? Can you see him?
Madam,
I will.
David, yeah.
Hello, Jagat. How are you?
Yeah, David.
That was wonderful, my friend. I was reminiscing. I was looking at old videos, and it was taking me back a long time to great memories. Thank you, thank you, thank you. Look,
yes,
as
David,
you know,
there was a question. Yeah. Could you please share what are the methods used to direct TBM to move in proposed path? That was a
look, the survey guidance is by laser. How you control and steer the TBM is by the jacking force on each one of these main jacks, whether you are thrusting off of the segments you have installed, or whether with this double shielded TBM, you are using the grippers in front and the thrusting jacks up ahead. But you are continuously monitoring the thrust, the torque, the RPM of the machine to ensure that you are going in the right direction. The control panel, the driver's cabin, just behind the TBM driving plate, shows all of this. You can see where your TBM is in real time. You can see its inclination, its orientation, its direction, and you follow this, and the driver drives the TBM according to this. It's not an easy job. It's a very skillful job operated by very skillful men.
Yes. Thank you, David. Yes. And there was another question by Mr. Viraj. Can you explain more about technical parameters of condylite rock? Have you encountered low strength properties of condylite rock during investigations? And what is the main cause of aggressive weathering of such rock? Condylite is actually garnetiferous granulitic gneiss, which contains pyrite as an accessory minerals. Pyrite is FeS2, ferrous sulfide. So this when the rock is exposed to air, this ferrous is converted into ferric and dissolved, and the ferric oxide precipitates, and the rock strength drastically reduced by this thing. And more importantly, the rock, when it is not exposed, it takes fairly longer time for weathering, but when the weathering started, it is the rate exponentially increased. So that's how this deep weathering occurs. So mainly this pyrite in this condylite rock get weathered. But regarding the strengths, of course, we have checked the strengths before weathering of fresh rocks. They are having appropriate strengths. So strength reduces only once the ferrous is leached out from the rock. I hope Mr. Viraj's question is answered.
Thank you, Dr. Gunatilaka. There's another question by Engineer Prabodha Jinasena. Can you see that when the tunnel trace?
When the tunnel trace was deviated from the original trace, won't there be any hydraulic issues inside? Wonder whether they have done any model studies to identify any. I think Mr. David would give an appropriate answer for that. David?
Yes, look, the curves were very gentle. The understanding of the hydraulics was certainly modeled. I think I answered a question earlier. The change in the trace of the tunnel was taken to try and avert the deeply weathered rock. We were in a syncline. You could see the high peaks of the syncline in the area. So the idea was to try and divert the tunnel under the higher points to gain more cover. The tunnel was also reduced in depth in these areas, but certainly the hydraulics of the tunnel was fully modeled and understood. It's a gravity flow tunnel from Direct Bar to the head of the pressure shaft, and there wasn't any problems with the diverted alignment in terms of hydraulics.
Right. Thank you, David.
Yeah, thank you. One engineer, Yoga Pragajan, has asked whether they could provide an opportunity for virtual field visit to Maui. Yes, of course. Water Forum has already contacted the project director, Engineer Alakanda, for that, and he has promised, as mentioned initially by Engineer Ruchini, we will have another seminar on that with more information and also with the virtual field visit. Okay, Dr. Gunatilaka, there is another question by Engineer Taraka Mayaduni. Can you please answer that?
If you mind, we can we know what is the current progress of the project? Are the public complaints solved now? I think, yesterday I had a discussion with the project director, Engineer Alakanda. Accordingly, actually, Badra Madam, Engineer Alakanda, project director is available. So, if so, he could answer it very well, no?
Yeah, I didn't see because he was having a meeting
right.
with,
So, so Taraka, the most of the public complaints are addressed already because huge spendings have been made to provide water for the affected people now. So they have now permanent water projects, or until the permanent projects reach their houses, they have provided water through bowsers and all this. The project, regarding the project components, the total tunnel is now completed, and the breakthrough was in last year, if I am correct. Yes. Still, grouting is in progress. Some part, I heard that the water flow along the tunnel has reduced up to about 200 liters per second. Now, that itself is a fairly good achievement, but it has to be further reduced to avoid these further environmental problems, of course.
Yeah, there is another question asking whether the original water table be established with time.
With time to its original level. That is very, very hard to answer this question, of course. If we seal all the leakage, seepages up to not 100%, maybe 90% or so, that has to be decided. So in such case, of course, yes, the original water table would be recovered within certain time period. It may take 10 or even 1 year. In case of Samanalava, it was only 1.5 years time, like that. But for certain areas, already water table has been recovered. But I'm doubt that some places, some areas, it will take at least 10-15 years to recover the original groundwater table.
Okay. Thank you very much, Dr. Guntila. I think you have spent more than 1.5 hours for us now. There are no other questions. Actually, other questions. Few other questions were there at the beginning through during the presentation, and Mr. Lees has answered all these things. I hope those were sufficient enough to those who are satisfied. I mean, the people who asked the questions. Thank you very much, Mr. Lees, once again. May I ask Engineer Kaushalya to wind up the session now with vote of thanks?
Madam, I'm Ruchini here. Thank you very much, Madam.
Yeah.
Now,
Ruchini,
yeah,
sorry.
now we are reaching to the end of this session. Thank you very much for all of you joining with us, and we highly appreciate comments and questions raised by you and your valuable participation throughout the session. With that, I cordially invite Engineer Renuka Gamage, representing Civil Engineering Sectional Committee, to deliver the vote of thanks and winding up the session. Over to you.
Thank you very much, Engineer Ruchini. I am Renuka Gamage from Civil Engineering Sectional Committee. I would like to express my sincere thanks for guest speaker Dr. Jagat Gunathilaka for sharing your valuable experience, knowledge, and opinion. On behalf of Civil Engineering Sectional Committee, I would like to appreciate very thank for you. The presentation was very informative. Thank you, Dr. Jagat Gunathilaka. We hope your continuous support for future activities in ISL. Thank you very much again. Secondly, my special thanks goes to Engineer Sudharma Alakanda, Project Director, Umaoya Multipurpose Development Project, for guiding and supporting to make this event success. I must mention my deep sense of appreciation to Engineer Bhadra Kamaladasa, Chairperson of the Water Forum, for organizing the event and by taking leading role and moderating question and answer session. I may like to express my gratitude to Engineer Kamala Gunawardana, member of Civil Engineering Sectional Committee and coordinator of the Knowledge Sharing Committee, for supporting webinar arrangements. I am also very grateful to Engineer Thirini Kaushalya, Secretary to the Water Forum, for organizing the event with the better coordination of all parties. I like to express my special thanks to Engineer Ruchini Chandrathilaka, member of Water Forum, to compare the event. And also, I would like to acknowledge IESL Secretariat, especially Mr. Mr. Chamara and Ms. Gayatri, for their support in logistic arrangement. I am also gratitude all participants for your active participation on behalf of Water Forum and Civil Engineering Sectional Committee. According to the Engineer Ruchini and Bhadra Madam, there will be a lecture series on Umaya Multipurpose Development Project. I would like to invite you all to join the presentations, upcoming presentations, and gather knowledge and experience from that. Thank you all. Thank you very much.
Thank you very much, Nilini. Thank you very much, Kaushalya, and thank you very much, Engineer Badra Kamaladasa, for organizing this. And thank you all who have commended the presentation and those who have asked questions and showing the interest on the presentation. It was a good opportunity for me to make such presentation for IESL. Thank you very much.
Thank you. Good night.
Thank you very much.
Dr. Daga.